Right, the third video in the series of rates. I'm going to do this practical, famous practical, of how does concentration affect the rate of a reaction. Now, the reaction we're going to use, sodium thiosulfate reacting with hydrochloric acid. And it reacts like that. Let me show you. So that is sodium thiosulfate solution. That is that. Sodium thiosulfate solution, sodium ions and thiosulfate ions. It's ionic. And here I've got hydrochloric acid. Hydrochloric acid is that. If I put some hydrochloric acid in, then you might be able to see that reaction going on there will get not transparent but cloudy. You see it going more and more cloudy. It's going more and more cloudy because we're getting sulfur made, and the sulfur made is pieces of sulfur, tiny pieces of sulfur, and the more and more sulfur we get, then it blocks the light and it stops us seeing through it. We get that sulfur precipitate solid, and it makes that cloudiness, which will, if you put something behind it, it will obscure anything behind it. That's the idea we use. And we use it with this practical. And there are two such practicals you need to get your mind around. One, today we're going to look at concentration, but we use the same idea to look at temperature. So get your mind around that reaction that happens. Sodium thiosulfate is a solution, hydrochloric acid is a solution. Mix the two solutions together, you get this sulfur solid, which is how we monitor the reaction by looking at how much sulfur will stop us seeing behind it. There will be some sulfur dioxide gas, but that gas dissolves. As it's made, we didn't see any fizzing. You may have expected some, but you don't always see fizzing if the gas dissolves. And the gas is in there, it dissolved into the water when it was made. And of course we get some water at the end. So learn that reaction, read that if you want. If it takes a long time to get the sulfur, then it's a slow reaction. If it's a small time to get the sulfur, it's a fast reaction. This is probably the hardest idea to take on board. The reciprocal. Now, the reciprocal means 1 over. 1 over the time of how long it takes to obscure the cross. 1 over the time. 1 over the time is our indicator of how fast or slow a reaction is. Let's go to the next slide. There. That's the apparatus set up. Sorry, let me put this down. The apparatus setup is that we're going to do the experiment in a conical flask. We're going to look from the top downwards towards the cross that's underneath, and we're going to time how long it takes to obscure the cross, and we measure the time it takes for a certain amount of precipitate to be formed, and with that time we are going to do 1 over the time to give us our concentration. So practical details. We're going to put 50 of thiosulfate. That's a concentration of what we start with. We're going to put 50 of it in a conical flask. Place a piece of paper with a cross on it under the flask. Add some hydrochloric acid and start timing. When there's been sufficient reaction to form so much sulfur that the cross is obscured, stop timing. Repeat the experiment with different amounts of thiosulfate and water to dilute the sodium thiosulfate to get experiments done at various concentrations. I'm going to do all of that. Before I do it, let me tell you, we need that kind of table, and when we start, we're going to put 50 of thiosulfate, so that concentration, going to put 50 and no water and 5 of acid, and time how long it takes. I'm going to calculate the concentration for you after I've done the practical. But basically, by changing the 50 to 40 and substituting 10 water or 20 water, 30 water, 40 water, that will give us different concentrations. 1, 2, 3, 4, 5. 5 different concentrations. And we're going to get 5 results. And 5, then we'll be able to get 5 crosses on a line graph. And then we should be able to talk about the line graph. Now, having worked out the time in seconds, we're going to do 1 over the time to work out the rate. And that's going to be the rate of our reaction at the end. So that you really do need that table to understand what you're doing. Anyway, let's do the practical and I'll show you. So I've got that table that I showed you, practical, ready here. I hope it's ready. I've never done all 5 together like this. And I'm sorry, I couldn't get hold of 5 stop clocks. So I'm going to do each one of the 5 experiments with a 30-second delay. And in that way, I'm hoping to get them all done. Experiment 1, I'll look at the board. Experiment 1 was the one that had 5, well, they've all got 5. So these small measuring cylinders are 5 of acid. 5 of acid, but then experiment 1 had 50 of thiosulfate. So this first lot of chemical, sodium thiosulfate, and the concentration, you need to know the concentration, 0.2 molar. 0.2 mole per litre sodium thiosulfate. So this is at 0.2 molar sodium thiosulfate into the experiment 1. Now this is 40 centimetre cubes of 0.2 molar into experiment 2. This is 30 into experiment 3. 20 centimetre cubes into experiment 4. 10 centimetre cubes in experiment 5. So that's the thiosulfate added. Now, in order to get the volume of 50 each time, I need to put the corresponding amount of water in. That is an empty beaker. Sorry, not an empty measuring cylinder. No water in the first experiment. 10 in the second. That total volume there is 50. 20 in the third, making a total volume of 50. 30 in the fourth, making a total volume of 50. And 40 centimetre cubes in the last one, making a total volume of 50. So they've all got a volume of 50 now, topped up with water, so the concentrations are different. That's 0.2 mole per litre. That one has been diluted a bit, that one's been diluted more and more and more. Now let's get into the dilution. This is 4/5. This is 5/5. This is the same concentration we started with, 0.2 mole per litre. This is 4/5 of 0.2. This is 3/5. This is 2/5. This is 1/5 of that 0.2 mole per litre that we started with. I'll put those into the table later. But what I'm trying to say is there are 5 different concentrations. Now we can start the reaction by putting these on the crosses. Show you these crosses. I've had the crosses photocopied so that they're all the same cross, and I've had them all laminated to stop water wetting them. So the same cross, laminated. It's important that the flasks are the same size because we want that height. We want the depth to be the same so that we can compare them. And then I've got 5 of acid in these small measuring cylinders, and I'm going to add the first one. There's a clock's coming up there now, and give it a little swirl. And that clock read 11:28. So 30 seconds later, I'm going to do this one. And 30 seconds later, I'm going to do this one, this one, this one. Now this one, can you see it going cloudy? Can you see it going? Right, that's 30 seconds. I want you to see that one going. Right, so that is like 50 seconds. 50 seconds. The third one after 30 more seconds. Can you see the second one now going cloudy with the sulfur precipitate? Let's put these so you know which ones they are. I'm going to add the acid to the next one now. That's the fourth one. Right, this, I can't see the cross now. I cannot see the cross, and therefore that's I'm losing it now. Is it 1 minute? 1 minute and 40 seconds. And then the third one is happening. If I look at the third one, I can just about see the cross, and I can see it, and oh my God, I cannot now see it at all. And therefore I take the time, which is 2 minutes 20 seconds. 2 minutes 20 seconds. And then we can focus on the last two. Let me show you the results. So I'm after this one now. We started the experiment at 11:28, and each one was a 30-second delay. That one was done at 11:28, so that is in fact 50 seconds time. This one, actually now that fourth one is gone. That fourth one is gone. Is what's the time now? 3 minutes 30 seconds. And then we just got the last one left. We've got this fifth one left to do. See the cross? We can see it. watch it just being obscured. So while you watch that, I'll do the calculation. So 1 minute 40 seconds is 100 seconds. But we started 30-second delay. So you need to take off 30 seconds. 100 take off 30 seconds is 70 seconds. This one, 2 minutes 20 is 120, and 20 makes 140. 140 take away 60. 120, 140 take away 60 would be 80 seconds. This one would take off 90 seconds. So 3 minutes is 180, 210. 210 take away 90 is 120 seconds. This final one, see the cross? I can still see it. I can still see it. Obviously, this is the least concentrated thiosulfate. So this is the one that is going to take the time. We're going to take off 120 seconds. We're going to remove 120 seconds from the final time when we cannot see it anymore. Swirling it won't make any difference. Indeed, to be a fair test, I should not have swirled it. I'm sorry. Just getting a bit impatient. One of the things to learn is patience, but I'm finding if I'm doing these videos, I'm more impatient when I'm recording than when I'm not. Right, I can still see it a little bit. I can still see the cross a little bit. And now I cannot see it now. So let's record that time. That time is 6 minutes. 6 minutes 20 seconds. So that's 380. 380 take away 120. 120 would give me a time of 260 seconds. I know that might seem a bit of a mess, but I'll tidy up on the board. Those are my results. And let's go back to the PowerPoint. I've done the practical. They were the practical details I went over before I did it. So let's have a look at the results table. I've put in the results that I got. I put those results in, and now what I need to do is to concentrate, I need to calculate the concentration. I need to calculate the concentration in each one of those 5 experiments. And this one's got no water. So 50 of no water means the concentration of sodium thiosulfate was just the same as what we started with. So we started with that concentration, 0.2 mole per litre. So that one, the first experiment, is 0.2 mole per litre concentration. And that's 5/5 of, because you've got 5 lots, no water, 5/5 of 0.2, the 0.2 is there. Experiment 2 had 10 of water diluting it. So the concentration of thiosulfate was 4/5. 1/5 was water. 4/5 of the concentration we started with. We started with 0.2. So 4/5 of 0.2 is 0.16 mole per litre. That's the units of concentration. Similarly, the third experiment, 3/5, 2/5, 1/5, giving us concentrations in blue down there that you can read off. These blue timings are the timings that I got when I did the practical. Now, 1 over, this is the reciprocal. When you do 1 over time, you do 1 over 50. 1 over 50 is 0.0200. Do it in your calculator. Now, that's hard to plot. So what I do is I multiply by 1,000. 1,000 times that is 20. And to get it back to the right number, times 10 to the minus 3. So multiply by 1,000, you get 20. Times 10 to the minus 3 is divided by 1,000. Gets you back to that numerically, times 10 to the minus 3 value is the same as that value before the equal sign. That is 1 over 50. 1 over 70 is that. 1 over 80 is that. 1 over 120 is that. 1 over 260 is that. And again, I multiply by 1,000 to get them into more manageable numbers. And then I plot them. Now the plot is quite interesting. I would normally plot whatever whatever I'm controlling. I normally plot it down here on the x-axis, and I'm controlling concentration, so I would plot rate versus concentration. However, when I've got some graphs up from the internet, they're the other way around. So I don't want you to be confused by that. You can do these whichever way around you want. And so I've done it the other way around. I've done concentration versus rate. And they are my values roughly. See, the concentrations were 20, 0.16, 0.12, 0.08, 0.04, and I got these values for 1 over the time. And that seemed, on my rough sketch, really quite a good experiment. But the important thing about it is it shows you straight line through the origin. Straight line through the origin means that the rate is directly proportional to the concentration. Directly proportional means if you double one, the other one will double, etc. On a less sophisticated level, you could say as the concentration increases, then the rate of reaction increases. So I would say that first observation, as concentration increases, so does rate, is valid, but that concentration is directly proportional to rate is more sophisticated and a better expression mathematically of how these two variables are linked in this experiment. Now, I got these off the internet. So these were the concentrations plotted against timings, and that you'd get a curve like that. It's only when you do concentration against 1 over the time, look there, 1 over the time, then these are rates. So the rate comes about by calculating 1 over the time. That practical with thiosulfate done comes up quite a lot on exam papers. We can use exactly the same experiment. Experimentally, we can use it to look at temperature variations. And what we do is out of those 5 experiments, choose one. Choose one, do that one 5 times, but do it at different temperatures. For the same reaction, thiosulfate with hydrochloric acid, the time the concentration, this time, the concentration of sodium thiosulfate is kept constant and the temperature of the solutions is changed using a Bunsen burner. The time taken is recorded, 1 over T is calculated, and a graph is plotted. Now, I don't propose to do all that again, but what I can show you is if you did it again, you'd get final graph. It would look like this. 1 over the time, that would be the rate, and the temperature would be whatever temperatures you've done your 5 experiments at. And you would get a straight line through the origin. That is a boy result. So I don't think the results look particularly good, but I want you to understand what experiment you could do, how you would do it. It's exactly the same experiment that I've demonstrated the concentrations with, except you vary the temperature and keep the concentration of thiosulfate constant across all 5 experiments. Well, those practicals that we do, they will help to reinforce the ideas of concentration, pressure, temperature, size of reacting pieces, and whether a catalyst is used or not. We have done a practical in year 9 where we used a catalyst with hydrogen peroxide. We used manganese 4 oxide catalyst to make oxygen. I have a previous video where we call it the elephant's toothpaste, where I have hydrogen peroxide with a spatula of potassium iodide as a great catalyst with some fairy washed up liquid, and it comes up, erupts like a volcano type toothpaste experiment, but it's a huge big toothpaste called the elephant's toothpaste. You can go back and look at that if you want, but basically there that uses a catalyst. I've not demonstrated anything using a catalyst, but we could pick anything that we thought was a catalyst and run 2 experiments, one alongside the other, where we use catalyst in one, we don't use catalyst in the other. We expect the catalyzed experiment to be faster. We don't expect the non-catalyzed experiment to be faster. We expect that to be slower, etc. Finally, let me look at these graphs in a bit more detail. Commonly, you are given graphs and you have to interpret them. And you have to understand them. The main thing I want you to look at is, if we've got a curve, and say you're looking at volume of gas or mass of the apparatus or mass loss, you'll get a curve. Look, like that. That's a curve. If you get a curve, then it's the steepness. It's the steepness or the gradient. At any point, the gradient, which will tell you what the rate of reaction is. Obviously, if you do 1 over time, you get rate, then it's not the gradient. But quite often, if you look at these graphs they give you on exam papers, the gradient tells you if it's a faster or a slower rate of reaction at that moment. So if you get a curve like that, at the beginning, the rate is a fast rate. And the rate slows down. It slows down, slow rate. And eventually, when it's horizontal, the rate has stopped. The reaction has stopped when the gradient is 0, when the curve is horizontal. So reaction stops there, slow rate there, fast rate there. So starts off fast and slows down and stops. That's normal for a reaction. Normal reaction rate is fastest at the beginning, when you've got most reactants, and then it will slow down until the reaction stops. Graph ideas. Look at the steepness. Look at the gradient. That will indicate rate of reaction. Faster reactions will have a steeper beginning and will reach the end of the reaction faster. Horizontal gradient 0 represents no reaction. Look at the last point on the graph. That last point on the graph often ties in with Moll's ideas about what quantity of reaction is happening overall. And to hammer home that point about what quantity and Moll's ideas, I've got an example. Here, I've got reaction A, reaction B, reaction C. This is the curve they give you. 50 of acid, that's 1 mole per litre, with loads of magnesium at 20 degrees. And what you've got to do is to draw curves for A, B and C. Now A, 25. You started with 50. A is 25. So half as much acid, twice the concentration. Look, concentration. So you've got double the concentration, half the volume. Now when you double the concentration, half the volume, that will give you exactly the same amount of hydrochloric acid. But the time is different because the temperature, 20 degrees, the temperature is the same, 20 degrees, 20 degrees. What's different is the concentration. The concentration of the acid is double. If the concentration is more, the rate of reaction will be faster. That will be a faster reaction. Not only have you got to think it's faster, where will it end? It will end at the same point because you've got the same quantity, so you've got the same number of moles of acid in total present. So A is that curve there. Faster reaction, but levels off at the same value. How about B? Well, B is 50, but half the concentration, so it's a slower reaction. 50 of half molar is half as much acid. If it's half as much acid, then you get half as much volume of hydrogen coming off finally. So half the moles of hydrogen are formed for B, which is that one, because the number of moles of acid is half what you had before. You can work out number of moles of acid, concentration multiplied by volume. Concentration is half of what you had there. The volume is the same, and therefore the number of moles of acid is half, and therefore the amount of reaction we're going to get is half, and therefore this, on this 1, 2, 3, 4 scale, the B ends at half the value of the black line they gave you, and it's crucial you understand that. Those kind of exam questions are very common. And finally, 50 of 1 molar, 50 of 1 molar, hydrochloric acid with excess at 10 degrees. Now that's a colder temperature, but the quantity of acid is the same as what you had up there. And therefore C ends at the same value because quantity of acid is the same, but it's a slower reaction and therefore is less steep. This one's less steep, slower. That one is more steep, faster. That one's half the value because you've got half the amount of acid, etc. This question brings home to you the things you should be thinking about when you're looking at graphs. You look at steepnesses, you look at where they end. And the only way to get around and get comfortable and confident with these kind of graphs is, believe it or not, do practice questions and practice the question, consolidate the ideas. End of the rates topic. Good luck.